Good afternoon, students. This is to continue on week number 3. Week number 3, part 2. So we're going to talk about diode equation. So in order for us to drive the equation for the diode, let's put a diode here. This is the PN region. We have a P depletion region consists of holes, and also we have a depletion region consists of all of these. This is the p-type, and this is the n-type. So usually the this is the depletion region width. Let's say this is XD, and usually the current or the electric field going in this direction, and most likely the current diffusion will go from p-type to n-type. This is current density diffusion, DIFF. And also for the current drift is going in this direction. So remember this. And I don't know if I mentioned it, but always you're gonna see in the diode equation or the depletion region on the n-type for the p holes, or the number of holes is greater than the number of electron or the width of the depletion area on the p side. Why? Because usually the doping on the p side is higher than the doping on the n side. That's why the depletion region on the n side for the number of holes is greater than the p-type. So let me put it in words. Doping on the p side is higher than the n side. That's why depletion area is wider on the n side. Okay, so usually, let's see, we have to, this is the minority carrier due to distance. So NP, let's say, and this is the so we will have the thermal equilibrium P and O. So usually So on the n side, because of the number of electron is highly doped on this side, so usually it's gonna start from here from the positive, going up, and on this side it's gonna go down, decreasing exponentially. So usually and the difference here in the width is because of the depletion region width. So this is the PN0 thermal equilibrium concentration on the N side, and also here is the NP0, which is the thermal equilibrium concentration on the P side. So usually this will be NP of X because it's exponentially, and this is Pn of X. So and here's the whole Ln. This is Lp. This is the whole diffusion length. And this is the electron diffusion length. And at this point, we have the NP negative XP. And at this point here, we have the PN XN. So from here to here, this is the difference in number of holes, and from here to here, this is the difference in the number of the electron on the N side. Okay, one thing to know, the number of electrons supplied by the diode is equal to the number of electron taken out of the diode by the source. So that means the minority holes concentration with respect to the time should not be changed. So I mean dPn dt is equal to 0 constant. So going back to the diode equation, so you have to know that the diode current equation is the relationship between the current and the voltage is always exponential. So increasing or decreasing at this time. So excess concentration, P naught N XN is equal to Pn XN Pn0, and the n P naught negative xp is equal to np negative xp and p0. For the diffusion equation, on the p side is equal to or not equal to d square p naught n of x dx square p naught xtp. So this is the mean recombination time, mean recombination time, and we have the p naught n of x is equal to pn0 e v vt minus 1 e negative x negative xn divided by lp. lp is the whole diffusion length on the n side. So in this case, lp is equal to square root dp tp. We can write this one as a wiggly from the top. And also to account for the electron diffusion length, Ln is equal to square root of dn, this is electron diffusion length, and this is holes diffusion length. So to continue on this, the total density, so it's usually the density on the p side due to xp plus density on the n side due to xn. So knowing that jpxp is equal to q dp pn0 divided by lp e v divided by vt minus 1 x minus xn divided by lp at the same. So also jn xn is equal to q dn pp0 ln ev divided by vt minus 1 e negative x minus xp by ln. So putting these together, substitute, let's say this is equation 1, equation 2, equation 3, substitute equation 2 and 3 in equation number 1. So we will get the total current density in the diode between the N side and P side is Q dP Pn0 divided by Lp plus Dn Pp0 divided by Ln So the current through the PN junction is I, current through a PN junction, I is equal to A J total. You're gonna substitute equation for A and J total. So we already have J, let's say this is equation number 4. This is equation number 4. Not equation number 4, J total from equation number 4. So we will get the I, or the current is IS EV VT minus 1, where IS is the scaling factor called the saturation current, where IS is the scaling factor called saturation current. So knowing that IS is equal to the cross-section area, A, multiplied with Ni squared, multiplied with T for temperature. This is the cross-sectional area multiplied with Q dP LPND plus dN ln NA. So those are the diffusion length, and those are the doping density on N side and P side. And the dN and dP are the diffusivity on the N side and the P side. So just to elaborate on, where is it? So usually the most likely what we dealt with is the whole diode current equation is to tell us how much current is going to be flowing when the positive voltage or the negative voltage is applied. So usually when it's positive voltage, it's the forward bias. When it's negative voltage, is the reverse bias. So for the short base diode, during saturation current, so the IS is equal to A Ni square multiplied with Q dP divided by the width for the depletion region on the N side multiplied with the doping density D plus dN divided by the width on the depletion area on the P side multiplied with the density. So if we I think I distinguished this is the Pn of x, this is Pn0 and P0. Okay, so usually this is at this point, this is xn, and at this point, this is the negative xp. So the further point here is the Wn, and here is the W negative Wp on the P side. Okay, let's solve one problem from the book. Let me get this ready so I can share the screen. Okay, we're working on gonna solve this problem. So problem 1.40 on page 98. Okay, so the two p-n junction having IS1 is equal to 1 FA and IS2 is equal to 5 FA are connected in series and forward biased. So most likely we have both of them are connected in series and in forward bias. That means the current is running through this side. Okay, this is D1, D2 are connected in series and forward bias versus a common IV source, 1 volt source. So most likely we have 1 volt. Assume VT is 26 milli MV. Find individual voltage drops as well as the common current. So we need to find, most likely we have V1, V2. So we need to find V1, V2. And also we need to find the common current, I. Hint, we need to use this formula. V is equal to VT ln I divided by IS. It's a straightforward so this is going to be 1 volts. Okay. Stop sharing. So first step we're going to take, so even though the currents running through a series of D1 and D2, both currents are the same, but at the same time, just to explain it more, I just want to say that the current on the first diode that running through the first diode is IS1, E V1 divided by Vt, and the current running through the second one, IS2E V1 divided by Vt, since they are in series, so there's both of them are equal to the common, which is IS1E V1 Vt, here's V2, sorry, is equal to IS2E V2 Vt. That's, so solving this further, so we have IS2 divided by IS1 is equal to E V1 minus V2 multiplied with Vt, multiplied both sides with Ln. So we get the Ln IS2 IS1 is equal to Vt V1 minus V2. So we have Vt, IS1, V1 and V2. That one is in question. So V1 minus V2 is equal to 0.026 ln 5/1, which is millivolts. So knowing that the voltage, sorry, I know someone should remind me to take it out. Okay, so we got V1 minus V2 is equal to 41.8. That means V1 is equal to 521 millivolts, and V2 is equal to 479 millivolts. And I know you want to ask why and how did we get this? We have this equation. I'm going to put this one here just to show you. V1 minus V2 is equal to 41 plus 8 millivolts. This is a series circuit, so most likely 1 volt is equal to V1 plus V2. So V1 plus V2 is equal to 1 volts. We have, to match these, it's going to be 1,000 millivolts. Now we have two equations with two unknowns, and we can account for the V1 and V2. So at this point, it's easy for us to account for I is equal to 10 to the negative 15 E 521, which is V1 divided by 26. We already have the Vt is equal to 503 Na. So this is IS1 or IS2 is the same thing. So all the currents are the same. This is part A. Let me share the screen for part B. Okay, part B. Okay, part B says if the diodes are connected in parallel and forward biased versus a common 1 milliamp source, find their individual current as well as the common voltage drop. Page 4. This is problem 1.40 on page 98, and I'm going to do B. So most likely there's a current source here, and both of these are forward biased, connected in parallel. And the current running through here, which is the value is 1 milliamp. 1 milliamp. Let's say this is D1, D2. So for sure there's V2, V1, and for sure I1 and I2. So we need to find the voltage, common voltage, and also the currents. So we have I1 is different than I2. Most likely we have I main, which is equal to 1 milliamp, is equal to I1 plus I2. And also from the equation we've solved in number 1, we have I1 divided by I2 is proportional for IS1 divided by IS2. And that ratio will be equal to 1/5, which is 0.2. So now we have I1 is equal to 0.16 milliamp, and I2 is equal to 0.83 milliamp. So two equations with two unknowns, and the voltage is equal to 26 ln I1 divided by 10 to the negative 15 is equal to, this is milli, 672 millivolts. So I'm gonna assign homework so you can start on it for or next time I'll assign homework part 2 for, let me check. Yeah, I can assign homework. Homework chapter 1. This is part 2. Due on, we set up the first. Let's do the 20. Yeah, you can do on the 25th, September 25th. It's Friday. And so it's going to be 27, 31, 34, 39, we did 40, 44, 47, and 48. We have one more part in chapter 1, and we should be done. Next week, I should be done with chapter 1, and we should talk about the test. All right, guys, take care. We'll see you next time.